In the annals of intellectual history, certain works stand as pivotal junctures, marking a decisive shift in our understanding of fundamental principles. George Boole's The Mathematical Analysis of Logic, published in 1847, undoubtedly occupies such a privileged position. This essay explores Boole's groundbreaking contribution, dissecting its genesis, central tenets, immediate impact, subsequent evolution, and enduring legacy. The intellectual climate preceding Boole's work was dominated by philosophical logic, largely inherited from Aristotle. This logic, while possessing profound conceptual depth, was fundamentally qualitative, relying on syllogisms and the analysis of categorical propositions. Mathematical tools, in their nascent stages of development, remained largely separate from the realm of logic. The prevailing view deemed logic a domain of philosophy and rhetoric, a system of thought far removed from the rigor and precision of mathematics. However, a growing interest in formalizing reasoning, sparked by the advancements in algebra, began to stir. Mathematicians, such as Augustus de Morgan, made preliminary forays into the algebra of relations, laying some of the groundwork for Boole's endeavors. The limitations of existing logical systems, particularly their incapacity to address complex inferences and multi-relational reasoning, presented an intellectual challenge. Boole, a self-taught mathematician, recognized these inadequacies and sought to bridge the gap between mathematics and logic. His vision was to transform logic into a formal system analogous to algebra, amenable to manipulation and calculation. Boole's mathematical analysis of logic presented a revolutionary approach. At its core, the work established a symbolic algebra for logic. This was achieved by representing logical propositions as equations, where symbols represented classes of objects or propositions. Boole introduced a symbolic notation, utilizing symbols like x, y, and z to represent classes. He defined fundamental operations such as logical conjunction, represented by multiplication, logical disjunction, or logical addition, and logical negation, represented as 1 minus the symbol. The constant symbols 0 and 1 represented the empty class and the universal class respectively. He then developed a set of axioms and rules of inference, allowing for the systematic manipulation of logical statements. He provided a mathematical framework, offering the capability to derive logical conclusions by algebraic means. One of his most striking contributions was the concept of Boolean variables, which could adopt one of two values, 0 or 1, representing truth or falsehood. His system allowed the expression of complex logical relationships in the form of algebraic equations. For example, the statement all as a BS was expressed as xy equals x, where x represented the class of is and y represented the class of BS. This allowed the formal representation and manipulation of arguments. The work included operations rules and theorems analogous to those of algebra. The system's power lay in its capacity to streamline, systematize, and mechanize logical reasoning. Complex logical problems could now be tackled by applying algebraic manipulations, reducing the need for intuitive leaps. The impact of Boole's work was immediately felt, though its full implications would take time to unfold. The book represented a watershed moment, signaling the birth of symbolic logic. It provided a powerful set of tools for formalizing and analyzing logical arguments, significantly advancing the study of logic. It offered a uniform method for manipulating statements. It proposed the possibility of automating logical reasoning. The creation of a formal system for logic, analogous to algebra, had never before been achieved. This formalization provided a means for the rigorous examination of arguments and inferences. The work's profound influence on mathematics ensured that logic was no longer a primarily philosophical domain. Boole's work also resonated with the burgeoning field of computer science. Moreover, Boole's system provided a new framework for formalizing the laws of thought, offering a deeper understanding of human cognition and reasoning. The reception of mathematical analysis of logic was initially mixed. Within the mathematical community, the novel application of algebraic techniques to logic raised understandable skepticism. Its formalism, while elegant, seemed at odds with the traditional, qualitative approach to logic. Some mathematicians found the algebra unfamiliar. Philosophers initially reacted with a degree of wariness. They were uncertain about the implications of formalizing logic using mathematical tools. However, as the utility and power of Boole's system became apparent, its reception gradually improved. The system's ability to solve complex logical problems gained recognition. Those who embraced its potential began working to refine, extend and apply Boole's eye. The influence of Boole's work spread rapidly, inspiring subsequent generations of logicians and mathematicians. Boole himself expanded on his ideas in his subsequent work, An Investigation of the Laws of Thought, published in 1854, which advanced the system of logic. His work provided the foundation for various developments in mathematical logic. The contributions of later logicians, such as Gottlob Frege, who built upon the foundations laid by Boole, led to the development of modern predicate logic, a more expressive and comprehensive system. The work of Charles Sanders Peirce, who further extended Boole's algebra to include relations, also advanced the field. The incorporation of truth functions and the development of higher-order logic greatly expanded the scope of logical analysis. Thanks to Boole's work played an instrumental role in shaping the development of computer science. The binary nature of Boolean algebra, with its true-false values, mirrored the on-off states of electronic switches. This eventually led to the design of digital circuits and the underlying principles of computer architecture. The development of these circuits and the concept of programming both used Boolean concepts. Boolean algebra, therefore, became a fundamental tool in the design of digital computers. The application of Boolean algebra is embedded in the processing, storage, and manipulation of data, powering the digital age. In addition, Boolean algebra has widespread application in information retrieval, artificial intelligence, and formal verification. The lasting legacy of Boole's contributions demonstrates its enduring importance. The true extent of the transformations Boole's work would trigger could scarcely have been envisioned in 1847. From its place in the history of logic as a foundational work, the influence spread through many other domains. Its success resides in the formalization of logic, the use of symbolic notation, and the introduction of a new set of axioms and rules of inference. These characteristics created the foundation for the development of symbolic logic. The precision and rigor that Boole brought to logic had far-reaching effects. Boole's work established the possibility of employing mathematical methods to formalize reasoning. He created an intellectual climate that would foster innovation. In conclusion, the mathematical analysis of logic represents a pivotal moment in the history of thought. Boole's revolutionary work transformed logic, making it a subject amenable to mathematical analysis, setting the stage for the development of modern formal logic, and profoundly influencing the development of computer science. His approach transformed the study of logic, creating a new field of inquiry. It also influenced the way in which we study information and computation. The work's impact continues to resonate today, shaping our understanding of logic, computation, and the nature of thought itself. The enduring influence of Boole's work underscores both his profound insights and his lasting contributions